Hi, my name is Christian Chin and this will be my Lab 1 Constant Velocity video report. The primary purpose of this lab is to apply Newton's second law, the momentum principle, in the real world, comparing real-world data to data collected through a simulated model. To do this, I will use the Tracker application to analyze the captured video and the GlowScript application to create a model based on the data found in the Tracker application. Then I will compare these two data sets in a position versus time graph created in Excel. I chose to record a video of a rolling cart, the object, along a metal rail set up in the physics lab room. The cart will roll for 43 frames or 1.433 seconds. I will calculate the object's initial velocity using the velocity update formula and the average velocity formula. Since we are assuming the object is moving at constant velocity, the momentum of the object, mass times velocity, will be constant. Therefore, the net force of the object, which is the derivative of the momentum, will be equal to 0. Thus, according to the velocity update formula, the initial velocity will be equal to the final velocity, since F net over m times delta t will be equal to 0. Knowing this, we can use the average velocity formula, where average velocity equals to change in position over change in time, to find the initial velocity of the object. I have set the object's initial position and time to be 0 meters at t equals 0 seconds, and the final position and time to be 0.008889 meters at 0.033 seconds, calculating the average velocity and the object's initial velocity to be 0.269 meters per second. Opening up the GlowScript code, I set the ball's mass to be 0.5 kilograms and the ball's position vector to have the x component of 0.269, which I calculated through the data in Tracker. Furthermore, I have set each time step to be every 0.1 seconds. To model this simulation with constant velocity, we must set the fnet vector equal to 0, 0, 0 in order to make the initial velocity equal to final velocity in the velocity update formula. To truly simulate the velocity and position of the object, we must change the velocity and position equations to model the velocity update and position update formulas. Thus, I have changed the second part to both of these coded equations, adding F net divided by ball mass multiplied by delta t to the velocity equation and ball velocity multiplied by delta t to the position equation. When you run the GlowScript program, it performs a while loop that executes the position update formula equation for each time interval until 1.433 seconds, which is the final time of the object's motion. A different position is calculated at each different time interval with the same velocity. As you can see, when I run this program, the ball moves right in the positive x direction, and the ball has constant velocity as the graph has a constant upward slope. Moving on to the comparisons of the model and experimental graphs. Although close, the experimental velocity is higher than the predicted model velocity, meaning the calculated velocity inputted into the model is lower than the average velocity of the experimental graph. Both graphs have positions that increase with time that are linear, displaying constant velocity. Thus, the graph of the model would not be a good prediction for the position of the object. I recognize that there may have been some possible sources of error as I completed this lab. The first error may have been choosing a time interval where the object's velocity deviated slightly from a constant velocity. Thus, the velocity calculated using experimental data that is used to calculate the model's data in the GlowScript may have been off. The second error may have occurred if I pushed the object with great force, which added a slight acceleration component. Thus, the calculations for velocity based on experimental data may have been off. The last error may have occurred if I had analyzed the captured video through Tracker inaccurately, since it's difficult to visually point the center of the object at each frame, creating an inaccurate dataset. Originally, I had made the choice for my object to move in the positive x direction. However, if I had chosen my object to move in the negative x direction, my position versus time graphs would be flipped upside down, meaning that each graph would have a negative slope and velocity would be negative. To answer the second equation, what does this mean? It is possible for you to say how many forces are added together to give zero net force, resulting in constant velocity in the case that I observed. Since I had to push a cart along a metal rail, I can conclude that I pushed with a force equal and opposite to the friction force on the cart, resulting in a net force of 0. In conclusion, by having an object move in a direction with supposed constant velocity, we can determine the initial velocity must equal to the final velocity according to Newton's second law. From this, it is possible to create a model to imitate the object using calculated velocity from experimental data. In this scenario, the model data and graph was slightly inaccurate. Thank you for listening to my lab report. I hope you have a great day or night.